Got William Taylor, is a security consultant with a background in embedded engineering and DevOps, and in this talk, looking to create a case study concerning Transit Gateway in AWS, where security consultants were able to communicate freely across an apparent network boundary. The title of the talk is Unexpected Leaks in AWS Transit Gateways. Please give William a warm welcome.
Thanks, everybody. Hello. Wow, final talk on the final day of the conference. Excellent effort for making it this far. You're all looking way fresher than I feel, but my voice only has to survive for another 20 minutes or so. Not used to holding a microphone, so if I keep moving it away from me, just start throwing things if you can't hear. So I'm going to be talking about leaky AWS transit gateways. I'm going to be walking through a security assessment that I did earlier this year. We're going to be looking at some of the issues that I found in that assessment, and we're going to try and look through some of the lessons learned from that. So a very brief introduction. My name is Will. I'm a security consultant at WithSecure. I'm based in New York, as you can tell from the accent. I have a few areas of interest, including mobile and Kubernetes security, and more poignantly for this talk, cloud security. Let's take a look at the scenario that we're going to be walking through. So one of our clients, they have a new deployment of sensitive compute resources. The idea of this project that they're doing is no one will have direct access to the compute instances. It's all obfuscated from them. Users will go into a user interface, whatever service or application they want to run, type in some stuff, and then those resources will be provisioned in the background and deployed into this AWS account. And so one of the key design aims of this project was the isolation of that compute. So it's sensitive, and they want it to be completely separate. No one's talking directly to it, no one can access it. That's the primary security concern of this project. Having just said that, the new deployment is temporarily connected to the old deployment. So this is a transition phase. They're designing a new deployment in a new region, but the old deployment is still running. And so if you already have some compute running in the old deployment, and then maybe there's an update and it needs more compute, maybe some of that is issued automatically into the new region. So there needs to be some controlled, limited communication between them. And yes, this is a transition phase, but in their roadmap that is 1 to 2 years, so this is going to be the situation for quite a while. And this is where we come in. So WithSecure were hired to do a security assessment to look at those security controls and see if they're effective in their aims. Let's look at the design of this project so we can see what we're dealing with. Here's our isolated account, and we have our VPC, and in our VPC we have our subnets, and these are our compute subnets. So when someone wants some new resources, this is where our EC2s get deployed. And as well as our compute subnets, here we have our egress subnets. So if stuff does need to be, traffic does need to go out, goes through these egress subnets. Each one of those in its own availability zone within the wider region. Now, so for most of the communication that those compute instances might need to do, they'll talk to AWS private link endpoints. So if they need any other AWS resources, or if they do need to talk to the internet for whatever reason, private link endpoints is where the majority of stuff is going to go. But we're not talking about that today. What we're interested in is this legacy account. So we have new one on the left, and on the right, the legacy account, same idea, compute being deployed in there across various subnets. And the way that we're going to connect the new and the old is with transit gateways. So here we have our transit gateway, and the transit gateway attachments are attached to each of the egress subnets. Then there's a second transit gateway those two appeared for traffic to go across, and then finally the traffic goes into the legacy account. So now we can see how the new and the old are going to be connected. Finally on this diagram, and most importantly, we have the network access control lists. So these are in the egress subnets, and the way these have been set up is very granular. For each of the subnets in the legacy account, there's a specific rule for that subnet explicitly denying all traffic. There also happens to be a deny all, as sort of a catch-all, but the principle behind it is, by default, everything is blocked, but you have each of those rules for each of those subnets, and then if there does need to be communication between the two, that particular rule for that particular subnet, that can be switched around to allow communication across the two accounts. So, we have our design, so it's fairly clear what the expected operation is here. So, part of the assessment, we've deployed an EC2 into the compute egress, into the compute subnet, I should say, sorry. We deployed it using the same technique that the customers of this account would use. So using that user interface, it gets deployed automatically. And then, yeah, if we try and communicate with anything in the legacy account, it's just going to hit those NACLs and it's not going to go any further. So nice and simple. So on our test, what's the easiest way to test for this? It's, we just run a simple Nmap scan against one of those EC2s running in the legacy account. So we had all the private IP addresses for those EC2s in the old account. So we pick one of those, run an Nmap scan, and the host's up. It can hit it, it can enumerate all ports. I'm communicating with it. So that's a bit weird. Let's check the subnet, run an Nmap scan against the whole subnet. Same thing, all hosts, all ports being enumerated. Finally, just for good luck, we're going to run it against all the IPs known in that legacy account. And just all hosts are up. We can talk to every single EC2, enumerate all the ports. This isn't what the expected outcome was. So, now we can move on to the investigation. Let's try and find out what's going on. Like, the design seems to make sense on the surface. We can see how the traffic's supposed to be flowing, but the evidence very much proves otherwise. So what's going on? First thing we do, we look at the AWS account. Maybe that our test EC2 is being deployed somewhere else somehow. Maybe it's been deployed to the legacy account. But no, it's all been in the right place as expected. Are there any other strange resources in that account or something strange? Can't see anything. Everything seems to be matching the diagram that we've just looked at. We also have access to the infrastructure as code, so we could look through that to see if there are any clues. But again, everything seems to be supporting the expectation. The diagram that we looked at seems to match the infrastructure as code. We can explicitly see those transit gateway attachments being attached to those egress subnets. So everything seems to be as expected. So the NACLs, it's got to be the NACLs, right? Because that's the network protection that's in place. That's what we're using to try and control our traffic flow. So we take a look at them. Is there a sneaky allow all rule with a high priority in there or something? But couldn't see anything like that. Checking through all the rules all makes sense. And we can see like there's a rule explicitly denying a certain IP, and then we can scan that IP and we can connect to it. So it's like these NACLs just aren't doing anything. Time for a Google. So go to the internet and start searching around, try to see if anyone's done anything similar, anyone's got any similar experiences. We found a blog post on an AWS support forum. Now, this person is doing something very similar to the design that we looked at before. So they have multiple subnets split by availability zone, 2 subnets in each availability zone, and then by their testing and the documentation, it's impossible to link 2 or more subnets to a transit gateway attachment. Now, what these people were trying to do in their project, they actually wanted the scenario that we have. They wanted all the subnets to be connected to that transit gateway to be able to do whatever they want to do, send the traffic. So we're achieving what they want to achieve, and they're confused why they can't do it. What are the responses? The subnet association is simply the subnet within the entire availability zone. The entire availability zone. That's the clue that's going to tell us what went wrong. Let's go back and look at our diagram. So this is what we had before, but from what we've just learned on the previous slide, there's something should be slightly different in our diagram. It actually makes more sense to depict the transit gateway attachments here on the availability zone. Now, if our transit gateway attachments are attached here on the availability zone, then those egress subnets, they're not doing anything. They basically don't exist. Now our traffic is just going straight from our compute network to the gateway attachment, straight across. So there we go. Now we can clearly see why we were able to hit all of those EC2s in the legacy account. So the compute subnets, they did have the NACLs, but anyone who's ever deployed anything in AWS knows that the NACLs by default are just set to allow all, and they were, quite often you'll find them, they stay that way because a lot of people use security groups, and so just leave the NACLs alone. But in this particular project, the NACLs are critical, but they were placed in the egress subnets, which have now gone, so now we just have allow all in the background there. What's the fix? How can we stop this happening? There's always a caveat when talking about fixes because it's very dependent on the client's needs, a particular project. Like there might be a reason why they're doing something in a particular way, but there's a very clear thing that we need to apply. Those NACLs should be in the compute subnet. There is actually in the documentation, there's sort of a throwaway line that does mention that the NACL should be applied where the compute is living. So that was one of the mistakes that was made in the design. And also if you are using NACLs, then don't use the default ones. They should always be actively set, not just using the default. Maybe VPC peering is an alternative, but that's a different technology, it's a different approach. That they might be able to do the same thing they want to do. Maybe they want to use transit gateways. Maybe you want separate compute and egress VPCs rather than trying to have the subnets as the network separator. You know, subnets are more commonly the logical separator. Maybe separate them into different VPCs. But yeah, the exact solution, that will depend on the client and what they want to achieve. But those NACLs, that's the key one. If you're going to use NACLs, make sure they're set properly. So the conclusion, the lessons learned, what do we take away from this? Strong design, strong start. So this client, they did design with security in mind, which is excellent. They weren't just thinking about it as an afterthought, they were thinking about it, how they were going to protect their system, and they did security design review, again, very valuable. So someone looked at it and was like, okay, yeah, this makes sense, this seems to do what we want it to do. But this use case really shows how crucial it is to do that practical testing, because everything on paper, everyone was thinking it's all fine, and then 2 minutes of practical testing, we can see that it's not actually the case. Everything was completely open. Dangers of dodgy documentation. I think that's a little unfair. I mainly kept that line in because I really like alliteration, but one of the things in the documents about transit gateways, they talk about how it's attached to one of the subnets, and that's what it appears to be. And then because of that, that sort of implies that the original design we looked at is the right way around. It's the right way how everything's set up. But again, if you read the documentation carefully, it does say that it's different, which is why I say it's a little bit unfair what I'm saying. But the takeaway is, if you're just relying on the documentation can be wrong, can be incomplete, can be confusing, so it's great, but just never rely on it too much. So one final slide. So I walked through this use case, but it's far from being unique. This happens all the time. So some slightly different examples of when testing revealed strange behaviors. There was another AWS account with EC2 deployment. All these EC2s had public IPs, and the security groups were set to allow all. By design, like that was necessary for their function. They wanted high throughput. So they were using IP tables to prevent TCP connections to protect those exposed EC2s. 799 of them, fine, couldn't connect. One, you could connect. Scanning with an Nmap, I could hit port 22, port 111, connect on SSH. And it turned out it was just this tiny error in the initialization script where that IP tables rule. There was no catch to see if it was successful or not. It just ran, just a simple bash script, and then if for whatever reason it failed, it just carried on and like nothing had happened. So on this particular instance, that IP table rule wasn't set, it remained open. And again, so doing that security assessment, it all seemed fine, but because we tested it, we found that one that was the exception. It's not just AWS. Occasionally Azure will throw up weird things at you. So we had an Azure account with sensitive compute, and they had a large number of network security groups to control the traffic in and out. So there were very, very like individual IPs, individual ports, they had loads of them. But then they also had this thing called a service tag. Now I'm giving the shortest introduction to service tags. Last year, a good friend and colleague of mine, Aled Mehta, who is in the audience today, gave a great talk at Cloud Village about it, so I encourage you to check that out and speak with him for more information about the service tags. But basically what it means is, if you set service tag rather than an IP, the compute in your network can talk directly to any Azure compute instance with a public IP, because Azure Cloud Service Tag basically means all of those IPs. So it permits that outbound connection, and suddenly you've got that outbound rule. And again, it was the design was done initially with the great intentions, but then they threw in this service tag that they didn't really understand, because very few people do, and outbound. And that's me. Thank you very much for listening.